Hello kittens, and this is Juan here from Scruffy Cat, and today we are going to design, that's a strong word because we're not going to be doing too much of the design ourselves. We're going to be taking some already designed circuits and we're going to tweak them like last time, and we're going to give it our own flair. We're going to make a dual ADSR / VCA combo. And so let's talk about the module and do a little bit of an overview. Okay, so right here, I have the first design. This is a schematic originally designed by Renee Schmitz. It's called the fastest ADSR envelope in the West. Originally, it was designed to work with like 1 or 2 meg pots, but I really want to use these sliders that are coming my way, and they're only 50K. So I've gone ahead and modified the circuit to account for that, so that we can get roughly the same results. So for the VCA, this one right here is a VCA. It's a circuit by TMW from Electric Druid. I chose this design because, my other options, there's plenty of designs for VCAs, and a lot of them require matched components, and this one is one of those designs that doesn't. Now, I did run into, some issues with this one because this is the first time that I'm really working with an OTA it's a little bit tricky, right? Because unlike a regular op amp, this doesn't output a voltage, it outputs a current, and it has an additional input, which is what we use to control the amplitude, but that input is also a current. So what that means is that this circuit needs to have a voltage to current converter, that's what this is, and a current to voltage converter, that's what this is, right? This chip really does not want signals with really large peak-to-peak values, right? Like it really doesn't like it above, I think, maybe a volt or 2 or something like that. In fact, if we look in here, we can kind of see that the max over here is only, in this simulation here, is only like 15 millivolts, and the min is negative 16 millivolts, where the actual signal is 5 volts plus minus 5 volts, right? And so if you don't attenuate this signal, which is what these 2 little resistors are doing, this voltage divider, if you don't do it, then what happens is that this starts distorting really, really, really bad. So let's talk about the circuit a little bit more now that I have it here in KiCad. So I've gone ahead and already made the circuit design here in KiCad. This is the ADSR schematic in this box right here, and this is the VCA. And as you notice, there is just one connection that I'm making between the two, and this is just so that I can have one normal path, but that same normal path can be broken, right? So it's not limited by that. That's why there's so many jacks in here. So some of the changes that I made here from the original circuit was the adjustment for the pot values, right? So because of that, a lot more things needed to be tweaked, a lot more component values. Like for example, these resistors right here, they were normally, I think, 200 ohms, now they're 22 ohms. And that just was by reading his René's article. He talks about the relationship between this resistor and the capacitor that we use for discharge, which is these 2 capacitors here. I've added a switch so we can switch between 2 different values, where one capacitor, this one right here, is 47 microfarads, and then this one's 4.7 microfarads, right? So we have that load of 10-to-1 ratio. If you want to experiment, this is where you can tweak some of those values, and then you either get larger or shorter stages in your envelope. I've added a push button so we can trigger it manually. So I wanted to have an inverted output. Normally when we invert the signal, we have starts at 0 volts, right? And then when we trigger it, this one goes down and it gets more negative, more negative, more negative. Now this is great, but what if instead you wanted something where like this normally sound, and when you click it, like the VCA, right? Like let's say I want the VCA to be open, and then maybe I want to use this as a way to duck a signal. We've did this in the previous build, so this should not really be too different here. Another change that we added over here, this is actually was a modification that Rich Holmes came up with. He has a blog post and a video which talks about some of this stuff. Go check it out. But what this does is this allows us to re-trigger the attack decay stage of the envelope, right? So let me go back to my circuit and show that in action. Here. And so basically what that does is this little bit right here. When it's triggered, it allows to re-trigger that attack decay. So as long as the sustain is high, or the sustain is still at that sustain level, we'll get a way to re-trigger this. Okay, so that's what that little mod does. Yeah, so the input, it's mixed. So we're gonna be able to have multiple inputs. Now this circuit right here is tuned to receive a CV signal that is from 0 to 5 volts. Now the ADSR is generating 0 to 10 volts. So in order to use it in here, we need to attenuate it. And that's what this is doing right here. This is just a little voltage divider that's giving me half the signal of what's coming in. It's scaling down to half. So if it's 0 to 10, we're gonna get 0 to 5. Other than that, the only other changes I made was just, add a few LEDs here and there for reference, and just tweak the values just to make sure that the output was within the spec for your rack. Okay, so we got to test this, right? So let's move over to the bench and see this thing in action. First thing I would like to show is the envelope. So that's this blue line right here. All right, so there is the attack, decay. Let's extend decay a little bit. And shorten it. All right, same with the release. And it's really long, so. Let's take a look at the inversion. All right, so when we invert it to ground, then we should see a mirror. That's the dark blue right there, a mirror, but underneath it, right? So if we trigger it, it's gonna look like that. Now the mod that I did is shifting the inverted version of the envelope and putting it so it sits on the positive side. So let's okay. All right, so next thing, let's take a look at this retrigger portion of it. So for that, let's get this back in view, this one back in view. So this is without the retrigger. This is what that would look like, right? But with the trigger, we just hold the sustain. we're actually retriggering that. Easier way to see is if we lower the sustain. See? Let's get rid of the envelopes for now. And let's take a look. I'm going to put the sustain all the way up to the highest and cut the attack and the decay. Sorry, the release, decay, and attack, so that we can just observe the waves. Because this is interesting, right? This is the difference between testing this in a simulator versus actually putting it up on the oscilloscope. We get to actually see the nuances of the components as opposed to what the idealized behavior that we get from the oscilloscope. Right, so as we can see here, that output, it's not quite a perfect triangle wave, right? And if we lower the frequency, right, we can see that it starts to distort. Right, now we're now at a 17 hertz, which is, you know, not even something, I mean, most of this we would filter out anyway. But when does it start distorting? Well, as far as I can tell, the real distortion, I think, at least on this triangle wave, starts at like around 60 hertz or so. But it's subtle underneath it, right? It's not until we get down in the 30s that it starts to be pretty bad. Okay, so what did we get out of that? We know that it's not a perfect circuit. There is some distortion happening, but that's okay, because I think that distortion adds a little bit of character to the sound. And so while in a lot of situations we don't want distortion in our circuits, especially if we are going for a very precise type of application, this is a circuit intended for music production, and that's a lot more forgiving. And in fact, I could argue that the distortion actually adds quite a bit of character to it. I like it, so we're gonna build it, but not today. Parts are en route, and yeah, PCBWay has offered to sponsor another project. Yay! So we'll be doing that. However, holidays delays mean that we have to hit the soldering iron in a future episode. Not gonna be today. But hey, you know what? Good things come to those who wait. By the way, PCBWay is having their end of the year holiday sale, so be sure to check the links below and take advantage of the sale before it goes away. So once the module is complete, I'm going to put all the files on GitHub for you guys. So if you want to stay in tune to that, make sure to subscribe. So you know when the files are available. They won't be available until the end of the next part. As always, I welcome your constructive feedback. So if you have some comments or questions or suggestions for improvements, leave a comment below. Yeah, microcontrollers are peeking over the horizon. So maybe next video we'll set up a developer environment, and then once this one is complete, we'll get on to making some different type of circuits and projects. With that, we have come to the end of this video. So thank you everyone so much for all your continued support and encouragement. And until next time, stay creative and be sure to ride that positive rail. Bye.